Hello, everyone. My name is Jennifer, and I will be presenting with my teammate, Roland, and we will be discussing the paper Algorithms for Causal Reasoning in Probability Trees, and it was written by DeepMind. So before getting started on the technicalities of the paper, there's a few interesting points to highlight. When I was going through this, I came across an article by Quantum Magazine with Judea Pearl in 2018. And Judea Pearl had his background. He had figured out how to program machines to associate a potential cause to a set of observable conditions. And he did that using Bayesian networks. For example, given a patient who returned from Africa with a fever and body aches, most likely the explanation was malaria. This is probabilistic association. But in 2018, he criticized a bit of the industry, saying that what needed to be asked was machines to question why and to teach them cause and effect. So why reasoning by association should be replaced by causal reasoning? Well, as you can see on the cartoon, a cute little comical way, I wish they didn't turn on that seatbelt so much. Every time they do, it gets bumpy. Shows kind of the inaccurate conclusions that can be reached just looking at correlation. And instead, his vision for how truly intelligence will think is replacing it with causal reasoning, that machines need the capacity to reason that malaria causes fever. So what is causal reasoning? It's actually a central cognitive competency that we develop at a very young age. And it's the ability to identify relationships between a cause and its effect. So what caused an outcome? Generally not interested in describing or predicting, but in explaining. So what if and why? As you can see to the right, does attendance cause higher grades, or does good grades cause better attendance? And as a side note, causation is a deep question and philosophers still really disagree about it. So Pearl has also added what we call a causal hierarchy, in a way to think about the data in a causal reasoning framework. This is also called a ladder, and it has 3 layers. The first one is associational, which is asking questions about the system as it currently is. And it uses conditional probability. So it's seeing the data. What is it? What does a symptom tell us about a disease? Interventional is taking the next step in more of a causal reasoning, and it's doing to make something happen. And it's replacing the variables. So what if we did something else? Or what if I do X? What does my probability look like now? So what if I take aspirin? Will my headache go away? And then the highest level, counterfactual, is an alternative world. It's imagining and trying to ask almost mathematically, well, what if I had acted completely different? Was it actually the aspirin that stopped my headache? Counterfactual is the most difficult in that it's almost trying to go back in time when we can't. For instance, in the medical industry, potentially wondering if a patient had died, what if we had done something different or they had another treatment? But unfortunately, you can't go back and resuscitate the dead patient. But using this approach is a way to try to recreate that reality.
So for this slide, Jen and I were talking. We always like to figure out who cares, right? What's the point of this paper? Like, what does it add to the field, or why should we, why should you guys pay attention? And so, on the left is what's called a Bayesian causal network, a very simple one, or BCN, and it's simply like X causes Y and Z affects both. And so I'll say it like this. So X is, what's the probability of me getting a date if I ask a girl, right? And then Z could be like a confounder, such as it's a dating event. It affects both of us. Now what using a probability tree versus the BCN is that it takes that and it turns it all into this tree. And so we can go from every single step, from the node to the Z, and then from Z to X, and then to Y. And so we can follow each step and see the probabilities in between. Next slide, please. And so And then here, this one is what's called a SCM, or a structural causal model, which looks even more intimidating than a BCM. And so using a probability tree, what it also does, it takes all that and it can still put it into, in the paper it says, a subjective interpretation of probability trees puts causal discovery on a firm formal ground, which is really cool because what makes it hard is trying to not only understand and map, but also to explain the different relationships at every single step. And it can get more complicated once you talk about counterfactuals or interventions, but using probability trees can kind of help us see, okay, at this stage or at this step, this happens, and it's easier to see on a probability tree than as you can see as an SCM on the left.
So that leads us to the probability trees. And a probability tree here, by definition, is a causal dependency. So from one node to the descendant node. So here we see X going to Y is expressed through that node. And it's that Y can cause an effect on Y. And for each of these paths, so for this here on the left, this shows no causal relationship. X has no impact on the outcome for Y, versus here we can see that it does have an impact on Y. So we thought we'd just give an example of a probability tree and of a way of representing all of the possible realizations or possible outcomes of an event. And here we're taking a sample size of patients, and they have the probability of being ill would be D equals 1. And if a patient takes a drug when she is ill, so if she receives a treatment or not, so T1 would be receiving the treatment, and whether or not the recoveries are, does she feel worse or better? And so it maps out, the relationship across each of these events. So for the algorithms that DeepMind has created, one of the few, or the first step is you have to import these probabilities. That's the only user input into the algorithm. So for here, you would just, use their functions, use your own probabilities. And for more complex situations, they do have an import that functions and can add these probabilities at a faster rate, but this is kind of a basic representation. And then from there, the algorithms do all of the calculations going forward.
Now, Mincuts, they represent events. So if we're looking at something very specific, that is, so for example, if you're looking at a probability of R equals 1, that part where it goes R equals 1, that's the Mincut, because that's all we're really focusing on. So there's all these different ways that we can look at it. Like for example, in the paper, if you look on the fourth line, probability of having disease, or D equals 1 and R equals 0. And then the opposite one below it is D equals 1 or R equals 0. And then the last one is D equals 1 preceding R equals 1.
Yeah, and the algorithm just calculates each of these probabilities for you. So this is just looking at the existing data that you have and then just trying to understand a little deeper about each of the events. It's your, as they call it, your baseline probabilities. And again, you just import each of their functions, and it gives you, if you want to look at where R equals 1, it gives you the output is that probability. So,
okay, so the first level is association or conditioning. So so as you can see on the left is the original tree, and then on the right is the second tree. And what I liked in the tutorial that they had, the code that they were giving, if we're focusing on R equals 1, R equals 1 is a true event, and so that's what we care about. That's what's green, and then R equals 0 is obviously it's the false. Now what's really cool is that the purple is it's called the critical event, And the way I remember critical event is that it's the node where there could be failure. So if I'm asking someone on the date, it's if I say the wrong thing, I could fail or she could say no. So every time there is a probability of something being false or the red square, that's where that comes out. Now, also, well, what happens too is when we condition on something, the algorithm takes out the probability. So if you look on the left, all the R zeros, right? There's a probability, like the very first one top right, there's a probability of 0.04 of that event occurring. But when we condition on R equals 1, that becomes 0. However, there's still a proportion that we have to keep with the probability. And so it renormalizes all the probabilities after conditioning. And that's why you see on all the other probabilities changing.
Yeah, because it removes the probability that doesn't meet that condition that you're trying to focus on. So the question that you're ultimately asking is, what is the probability of event A given that, say, event B is true? So this is like a first step in approaching, kind of this causal reasoning framework. And again, this is just, we wanted to just show the snippet of pretty much how easy the algorithms are to use. And then the second step moves on to intervention. And this is really the heart of causal reasoning. And it is basically performing an exogenous event onto the system. So asking questions like, what is the probability of event A given that event B was made true? And so as you can see here, it's similar in the sense from association, but it only looks at, it doesn't change the partial probabilities or the transitional probabilities unless whatever it is that you're trying to make an intervention on. So we're intervening here on saying that this notation T means that the shorthand is for T equals 1. So if there was treatment that was given.
Yeah, so everything before, and an intervention, everything before the critical event, the purple square, stays the same. So it kind of makes sense. Like, so, everything's going on, and then we change one thing. So we're saying, so instead of association or conditioning, now we're saying we're literally changing this. So the only probabilities that change are everything after that event.
Right. And then counterfactuals, which is the most kind of complex and kind of the interesting, the highest layer of that hierarchy. And this was a good quote. We think of a cause as something that makes a difference, and the difference it makes must be a difference from what would have happened without it, had it been absent its effects, and some of them at least, and usually all would have been absent as well. So counterfactuals are questions about how the experiment could have gone if something about it were different. And there's two types of statements, things that happened and things that had happened in what we call this alternative reality. Given that B is true, what would the probability of A be if C were true? And counterfactuals will spawn a whole new random variables that were not there. And
I know Jen talked about an example earlier, because for me, counterfactuals always kind of made my head spin. I'm like, why are they important? And so an old mentor of mine told me about one that kind of sticks to me, in terms of smoking. Like, how do we know that smoking causes lung cancer? Because obviously what we want to use is an RCT or randomized controlled trial, so we can control for all the confounding variables, so we can say that this causes this. So we can say that smoking causes lung cancer. Except we cannot make randomized controlled trials and have people smoke and another population not smoke. So what they used was they made a counterfactual world where they said, okay, if these smokers who had lung cancer didn't smoke, what would have happened? And from there, that's how they came to their causal reasonings.
Yes, so as we can see here, there's, for counterfactuals, we create these D asterisks and R asterisks. So for the drug and recovery, they're copies of the original random variables, D, but that they're occurring in this kind of new, different reality. And so this is an example of this top left baseline is the original probabilities that we had set. So if we were looking at R equals 1, so for recovery, the probability is 0.5 for our baseline. And then for our premise and counterfactual, we're asking, given that I have taken the treatment and I have recovered. So in this, on this top right, premise is I have taken the treatment and I've recovered, so R equals 1. Then we intervene on the probability tree. It resets the probabilities of having the disease from 0.4 to 1.4 and 0.6 to 0.857. And the idea behind that math is it's looking at the original baseline, and it's saying that if you received the treatment and you recovered, and if you didn't have the disease, it was 0.04 was the probability. But if you did have the disease and you did get the treatment and you did get a recovery, it was a significantly higher probability. And so when it renormalizes to account for that, it resets the probability of having the disease is going to be a lot lower of not having the disease than having the disease. And so it recalculates and says that basically I'm assuming that you had the disease, you received the treatment, and you recovered. And so therefore you had, a high chance of recovering, a high probability. In the counterfactual world, we're trying to look at, okay, if I actually recovered, or what is the probability of recovering had I not taken that treatment? And so that probability drops down to 0.28, given that you probably didn't need the treatment. Yeah, I believe. Yeah. So as you can see here, it's able to take, counterfactual is able to take from our baseline probabilities that we set, and it's able to kind of recalculate this false reality to some degree to give you some sense of a new probability.
And so what I also want to mention too are what are the limitations of a probability tree? Because we've seen the trees built with like maybe 3 variables, right? And for our work, for example, in causal inference, we have multiple features, some like maybe 60, 70, if not more. And so trying to make a probability tree that we can see everything out of is it won't fit the screen. So in that sense, a BCN, the first picture that we showed is more concise, and it can kind of give you a more concise picture versus a probability tree. And in the paper too, they talked about that they have more future development that they wanted to add to it, like temporal logic, probabilistic programming. They talked about identification, such as, and that means like whether a cause and effect can be estimated from observation alone. So this is an exciting thing that they started, but they wanted to show how